Good morning. Today we'll see about the behavior of protective CT, and also we will see the circuit model of a saturated CT. So in the last class we have discussed about the different faults on the bus bars. We have seen that based upon the differential protection we have classified the faults as internal faults and also external faults, and we have seen that the non-ideal CTs, in our case we call them as saturated CTs. The saturated CTs pose a threat to the differential scheme, and we have also seen how they behave for external and internal faults. The differential protection must protect the device or the bus bar in this case for internal faults, but a saturated CT will create a maloperation and will trigger the alarm even in the case of external faults. That we have seen in the last lecture. So in this lecture, I hope that by the end of this lecture, you will be able to describe the behavior of a protective CT and also develop a circuit model for a saturated CT. How to represent the saturation in the equivalent circuit of a transformer. Now, I'll start with the basic CT, the equivalent circuit of a CT. See, this is the equivalent circuit of any transformer. In our case, it is a current transformer, but any transformer, you know that any transformer basically will be having two windings, right? I'll take a two-winding transformer. There may be a three-winding transformer, auto transformer also, but let us confine ourselves to a two-winding transformer, right? So either of the two windings will be having a resistance and an equivalent leakage reactance, right? Right. So these are the, or you can represent it as primary and secondary also. So this is the resistances of the primary and secondary windings, whereas these are the leakage reactances of the primary and secondary windings. And apart from that, there will be a magnetization losses representation, right? These are the magnetic losses representation. One indicates magnetization, the other one indicates loss, core loss. So I'll represent them as R0 and X0. This is the actual representation of any transformer, equivalent circuit of a transformer. Now you can refer these things to either of the sides, right? So what I am doing here is nothing but I am just referring these things to the other side. So I am just transforming them. See, this is my right. So these are the primary side which are referred to my secondary side. And these two, they represent the secondary side also. So no change, right? So this is my circuit which I have represented here. So the input now, since this is a CT, the input is going to be IP. So based upon the CT ratio of N:1, we will be getting a secondary current, IP by N. And this is equal to IP by N is equal to I0. A small amount of magnetization current. Most of the times it will be somewhere around 1% to 5%. In normal cases, I0 plus IS. Right? I am applying this KCL here. Three parts. So if I want IS is nothing but I0, IP by N minus I0. Okay. And this is the burden of the CT. Now, this current which is flowing here, IP by N, which is creating a magnetizing circuit, which is providing the magnetic field. So the amount of current which is wasted, I will refer to as I0. And this in turn is responsible for development of EMF here, which in turn provides you Vs. So now in this case, so these are the representations. I have just mentioned the notations. Okay, we can go through them. So this is the equivalent circuits. So if I remove the second, I'm just neglecting this one, and I'm just representing it as a current source here, IP by N. Okay, so this is my IP by N, which is resulting in a current of I0, which in turn develops E, and also this is the current which is flowing in this circuit, IS. So if I remove this one also, see, if I consider only this particular circuit, so what is the current which is flowing here? IS is the current which is equal to IP by N, and here what is the, there is a small resistance and a reactance, right? RS and XS, and this is the Z burden. This is what I am representing here, Z burden plus RS plus JXS. So this is the simple circuit. This is the total Z burden plus RS plus JXS. Now this is the equivalent circuit of a CT now, right? So normally what happens is at lower values of primary current, what will happen? If the currents are very low, IP is low, IP by N will also be low. So I0 also will be low. So IS also will be low. So if IP is low, automatically I0 will be low, and also IS will be low, and also since IS is low, Vs is low, which indicates that E is also low. Right. So everything is smooth and as per the ratings. So, and the working flux, see the flux which is there. Flux is, you know that in a transformer, E is equal to 4.44 F En phi, right? So my flux is equal to E by 4.44 F N, and I am considering here in this case only one term is there, so I'll just represent it as this. So if EMF is low, then automatically flux is also low. So ultimately, see here, if your primary current is low, then ultimately your flux is also very low. Now, if you slowly start increasing the current, let us suppose if there is a fault in the system. If your fault is there in the system, then automatically what happens is the secondary current will increase substantially, right? So the secondary current is increasing. Now let us suppose if there is a fault, or maybe we will consider if IP is increasing. So automatically what happens? IS also increases, right? If IS increases, automatically what happens? Secondary induced, right? Vs and also Es will increase. If Es increases, what will happen? Flux will increase, right? Flux is equal to E by 4.44 F into N, right? So flux is increasing. If flux increases, what is, to set up more amount of flux, what do you require? You do require maximum amount of magnetism. So I0 is going to increase. If I0 increases, what will happen next? Where it is coming from? You know that IP is equal to I0 plus IS, right? So earlier in this case, since IP increased, IS increased, and this is created a cumulative reaction. Ultimately, what is increasing? I0 is increasing. If I0 increases, automatically what happens? IS is going to decrease. This is what I will explain you. See, if I0 goes on increasing, see, the higher the amount of magnetic flux is required, then automatically I0 increases. Normally, you might be taught this BH curve. Have you ever heard about this BH curve, right? It will be like this, right? You would have seen this BH curve, right? This is the magnetizing force which you do have to set up to develop this amount of magnetic flux. So initially the curve will be linear in nature. As the current slowly increases, the magnetic flux will be developed. But after some time, the magnetic flux, even for a small change in magnetic flux, you do require large amount of increase in current, right? It's because it has become saturated. So after some time, if you go on increasing the IP, if you go on increasing the IS, to increase this phi, you do require large amount of I0. Where does this come from? This should come from IP only. So automatically it will lead to decrease of IS. See, this is the magnetizing curve. So initial cases as flux is small, I naught requirement is also very small. But after that, for a small change in flux, you do require a large increase in I naught. See, this is the problem. So at higher values of IP, automatically what happens? This will lead to decrease of IS. So this phenomena is observed because of your saturation. Because at higher values of B, which means it is moving into saturation, see, this is my IP current, primary current. So it will be sinusoidal in nature, right? But in this ideal case, if this is if this is IP, my IS also will be a little bit lower than this one. The difference is nothing but your magnetizing current. But in this case, see, it has reached to saturation, so it requires huge amount of magnetizing current. See, whatever the current which you are injecting here, it is being drawn as a magnetizing current rather than as your what I call secondary. So that's fine. See, since flux is constant, flux has moved into saturation mode because my saturation has been done. Since it is being saturated, automatically what happens? You know the EMF which is developed, it is proportional to d phi by dt, right? Flux, there is no change in flux because it has become saturated. So automatically what happens? Since it has saturated, there won't be any EMF. See, here, since flux was slowly increasing, there was an EMF. But after that, there is no increase in flux. Transformer has get saturated. So my EMF has become 0. Since the EMF is 0, the current also will be 0. So that's why the secondary currents on the CT, they will be just not looking like a sinusoidal, but they will be looking like a spikes. Just instead of a sinusoidal secondary current, what you see is nothing but just a small spikes of the currents. So this is what happens when a CT becomes saturated. This happens because of huge amount of drawing of magnetizing current, and ultimately what you see, I have mentioned it, when all the transformed current is taken up by the CT for the sole purpose of magnetization, and there is hardly any current available for the meeting the burden. So when this occurs, we say that CT is completely saturated. In the secondary induced voltage and burden current waveforms, they are highly distorted. And in fact, you can see only sharp pulses near the zero crossings of the primary currents. And due to the flatness of excitation, the flux curve you have seen, large amount of exciting current is being drawn. So, which means that you are not getting any current. Which means maximum current is being drawn here itself. That's why instead of representing it, earlier we used it to represent it as in this fashion, magnetized. But since it is itself drawing huge amount of current, what I am doing, I am just representing it with a short circuits. So this is the true representation, the best representation of a saturated CT. See, shorting of your magnetic circuit because there is no current available for the burden. Okay. So the magnetizing branch is replaced with a short circuit to signify the fact that magnetizing branch is taking up all of the secondary current and nothing is available for the burden. So your circuit model now consists of a source value of IPN, which is feeding into a short circuit of RP dash and XP dash, which are equivalent resistance and reactances referred to the secondary of the primary. And the connections to the outside world are available through RS and XS. Okay. So the conclusion, what is the conclusion of this one? A saturated CT is modeled with its magnetizing circuit as short circuits, and this leads to minimal or zero current at the load terminals. You will hardly find any current to meet here, but so I hope that now you have understood how to model a saturated CT for your power system analysis. And these are the short answer questions. You first explain the behavior of protective CT and develop the circuit model of ideal protective CT, and then you do the analysis and develop the circuit model for a saturated CT. Okay, so that's it from my side. Thank you. In the next class, we will see the significance of saturated CT and how different ratings are affected.